speaker is Dan Chavas from Purdue University, where he just started there a month ago. Before that, Dan got his undergrad degree in atmospheric science and applied math from the University of Wisconsin in Madison. And then he went on to get his PhD in atmospheric science from MIT, and then spent the previous 2 years before heading to Purdue as an NSF postdoc at Princeton in civil and environmental engineering. And so today, Dan's going to talk to us about tropical cyclone wind field and its variability. Go ahead and get started.
There we go. Is that working? All right. Thanks, Kevin. Thanks to all of you guys for coming out today. Appreciate it. Thanks for inviting me for the seminar. So yeah, I'll be talking about the wind field, particularly the low-level wind field of a tropical cyclone and its variability. It's something that for most of the work in our field has focused, when we talk about tropical cyclones, hurricanes, have been interested in what we call the intensity, which is generally taken as the peak wind speed. And almost all of the work that's been done has been focused on that topic. And so my interests for the last several years have been on understanding the full wind field itself. And so I'll talk about that. And just as an intro, I just like to start with this image. In the background, this is a visible satellite image from the 7th of November 2013. And it's at sunrise. And this is Typhoon Haiyan in the West Pacific right before landfall at the Philippines. And it's really a beautiful image of a very terrifying storm. But I just think it's remarkable. You have the eye here, and then you can see the sun catching the upper western, or the western edge of the top of the eye wall of the storm just before landfall. Okay, so this is to sort of wake everyone up. Is it playing sound? Oh, yeah, it is. Okay, there we go. This is a movie from YouTube from somebody who was not me, thankfully. This is the storm surge from Typhoon Haiyan somewhere in the Philippines. We'll play it one more time. This is sort of motivation, but also just kind of a remarkable movie of the power of hurricanes and particularly what the low-level wind field can do. And so I don't know. I hope the person who took this video was okay, but I don't actually know. So I just show this really just because the low-level wind field is critical and really in two different respects. One is in terms of the physics of hurricanes, which is what I'm interested in, what I'm talking about here, is that hurricanes depend on the exchange of enthalpy and momentum with the ocean surface, so particularly evaporation. So in some sense, you can see there's lots of exchange of water and momentum with the surface. And then, of course, for damage, is that the wind field causes damage directly. It also drives storm surge that causes damage. And so we really, from both perspectives, we'd like to understand the wind field, the low-level wind field of a storm. And in particular, we know increasingly well, and I'm sure you guys now know here very well, is that damage risk really depends on a lot more than just the peak wind speed. So what this has shown is something I'll show a lot of today, which is radial profiles of the wind. So wind as a function of radius for 3 different storms: Camille in '69, Katrina in 2005, and Sandy in 2012, all of which caused many billions of dollars in damage. So it's not relevant. You know, it's not a comparison of billions. They all caused an enormous amount of damage. And often people have focused on the peak wind speed. And you can see that these are 3 storms with very different peak wind speeds. But they also come in at very different sizes. And so focusing just on the peak wind speed doesn't tell you a lot. Well, it tells you something, but not enough information about what the potential is for damage. So in particular for Sandy, we know that the peak wind speed was relatively low, and still it caused a tremendous amount of damage. So we'd like to understand the wind field in general. So first, just to start off with a very basic primer to get everyone on the same page. So this is a visible satellite image, just of a canonical hurricane with the eye at the center, and then it's very circularly symmetric with most of the rain and clouds just outside of the eye and the eye wall and near and small radii outside of that. And so this is just a 3-dimensional transect, idealized hurricane essentially of where the colors denote the rotating winds. So the winds are rotating very rapidly, and in particular, they're strongest near the surface and at small radii. And so we can think of, to first order, is that a mature storm is nearly axis symmetric, which means we can think in terms of principally of quantities as a function of radius. And so we're interested in how the wind field near the surface varies, moving radially outward from the center of the storm. OK, so just basic outline. So I'm going to talk first about just from observational from observations, what does the wind field look like, and how does it vary? What does that look like? Can we characterize that? And then understand the structure. Can we understand the complete structure, which I'll define a little bit more in a second? And then understand how the wind field varies. And this is a model that I'll be presenting. It's an analytical model to see if we can explain, or at least model, how the wind field the wind field varies in reality. OK, so first, just a simple point is that the wind field extends very far from the center. We often think about the winds near the center of the storm, but I'll argue that it's actually quite useful and perhaps fundamental to understand the wind field at far away from the center of the storm as well. So this is just a GOES 12 IR image of Hurricane Katrina. And at approximately the same time, this is, I think, 3 hours earlier, this is the wind field at the surface as seen by the QuickScat satellite. And so again, you see the winds, the center of the storm, the winds are very strong, and then they decay, moving radially away from the center. So if you compare sort of the cloud shield area where we would see, OK, this is how big the storm is, that certainly encapsulates where the winds are the strongest. But if you go farther out, you can see that winds at something in the teens and below 10 miles an hour, or 10, meters per second, extends quite far from the storm, from the center of the storm. We usually don't think about these things. OK, so this is what I'll be working with. I have actually, just to introduce 2 data sets that I'll be working with for the low-level wind field at about 10 meters height, is what they're both valid. One is in the inner core region. I'll be working with H-wind, which is a data set from going back to Powell et al. 1988. And it's basically an optimal interpolation of all available data at 6-kilometer resolution in a fixed size box that's, I think, 800 by 800 kilometers. And then for outer region data, I work with the QuickScat satellite data, which is best for low and moderate wind speeds. And so this is, I'm actually working with the data set we put together of radial profiles of the wind from QuickScat called QSCAT-R. And it's basically, this is a scatterometer-based data set that has a 12.5 kilometer horizontal resolution, where the satellite is just shooting radiation to the surface and looking at its reflection based on small-scale capillary waves. And that tells you something about the wind speed near the surface. So, and this is a product out of NASA JPL. OK, so the same case, the Katrina case that I just shown, we can start look at the radial profile of the wind. And specifically, we're interested in looking at the azimuthal mean, so which is the radial profile of the azimuthal wind, so the rotating wind around the center of the storm. And so what does that look like for the case that I had shown just a couple of slides before? It looks like this. So again, azimuthal wind is a function of radius. And what I've done is basically combined, I've taken H-wind data in the inner region and then QuickScat data in the outer region. And you see this longer tail. So let's deconstruct this so we can understand our terminology. Intensity is the common one, which is called Vmax, the maximum wind speed. Size, you could think of as the radius of maximum wind, so the radius of Vmax, though it's sort of ambiguous, and I'll come back to that. And then structure is sort of everything else. How do things change with radius, so DDR. And so in this case, I just want to point out that you have this sort of 2-region structure. You have this rapid decrease just beyond the radius of maximum wind. And then at larger radii, you have this long tail. And it goes out here. We're going out to up to 1,000 kilometers here, and the winds are still appreciably above 0. So that's one thing we'd like to understand. We also like to understand, how does this vary? So how does this profile vary? And so what we can do is just to take some examples. So this is, again, select cases where I have both H-wind and QuickScat data that are relatively close together in time, and I can put them together. And so this is a set of 4 cases where this is Emily, Ike, Francis, and Ivan from different years, and these are just wind profiles from each of them. And so what you'll notice is that you have this common structure, again, this rapid decrease beyond the radius of maximum wind, and then the long tail. But they all occur at different sizes. And the size concept varies really at all radii. So these are storms that are similar intensities, but they're showing up at different sizes. So no matter what wind radius you look at, 12 meters per second, something like that, they're all consistently at different sizes. And this is something that's been known for a little while, but hasn't really been looked at in terms of the full wind profile. And then here's just another example. This is Charlie, Ophelia, and Ike from different years. And this is at just a lower intensity, essentially. And again, you see the same thing. You see similar structures, but at different sizes. So you can think of this mode of variability as size. So similar structure, different sizes is one mode of variability that we see commonly in nature. So additionally, we can look at, here's 3 cases from Ike, Ivan, and Katrina from different years, where in this case now we have a very, very similar outer circulation. They're very comparable outer circulations here across all 3 of these storms, but then a highly variable inner core. And so in particular, what you're seeing is that this inner core, so as the intensity at higher intensity, the radius of maximum wind decreases. And so this variability, this large degree of variability is occurring where the outer circulation is basically exactly the same across all of them. And this is something that actually goes back to Weatherford and Gray in 1988. It's been understood that they sort of pointed out when they looked at observations that the inner circulation seems to be able to vary while the outer circulation doesn't care at all. It doesn't seem to notice what's going on. So, and then additionally, I want to point out, as I said, this term size is actually ambiguous. If you define it as the radius of maximum wind, which you might, if you're interested, for example, in damage, you care about the radius of maximum wind. Here, size is varying. But if you pick something from the outer region, say the radius of 12 meters per second out here, the size is basically the same across all of these cases. So this is one thing that's been a struggle for some time. When we talk about size, we're often talking about different quantities. And so for my purposes, I'm particularly interested in size of the overall circulation of the storm. But it depends on your interest. So what I'll call this is just variability mode number 2, which is structure and specifically associated with changes in intensity relative to a fixed overall size of the circulation. OK, so you can just put this together. This is just a whole bunch of cases now, just kind of plopped on top of each other. There's 31 cases where you see maybe it's a little bit more of a mess, but again, there's this really consistent structure. We have this rapid decrease followed by the long tail. And so what we'd like is a model for this complete structure with those 2 components. And then also, we'd like to be able to understand the variability. Can we have a model that represents these modes of variability? And again, this idea that you have size variability of the overall circulation, and then you also have structural variability in the inner core relative to a stable outer circulation. So let's start with structure. OK, so first, I just want to start off that these ideas are going to come not by thinking about the wind field itself, but by thinking about the quantity absolute angular momentum, which is really a more fundamental physical quantity. That's something that has to be conserved away from, say, boundaries. And so this on the right is just the same profile from Katrina. In blue is the wind profile, and then in red is the profile of absolute angular momentum, which necessarily has to increase with radius. And it has 2 components. There's the relative angular momentum component, which is associated with the hurricane. And then there's the component associated with the rotation of the Earth. And I should point out just more in general, hurricanes are basically acting to take angular momentum from the Earth and convert it to its own circulation. And I'll come back to that later as well. So the idea, though, is that we actually have existing analytical solutions for this quantity m that's valid for the gradient wind at the top of the boundary layer that apply for 2 distinct regions, an inner region and an outer region. And so what I'm going to be doing is trying to merge those 2 things together and see what that gives us. So first is the inner ascending solution from Emanuel and Rotuno in 2011. And I call it ascending because it's really valid in the region where there's mean upward motion, sort of some time mean upward motion. So there's persistent deep convection going on there. And so it's shown here as, again, a 3-dimensional transect. And this is now radial velocity, just to show that you have this overturning circulation. So you have this small band where there's strong radial inflow, and then ascent, and then there's radial outflow aloft. This is a common overturning circulation as part of a hurricane. And so the physics of this solution are such that basically they're complicated. I'm not going to go in great detail, but essentially it's tied to the notion that there's small-scale turbulence in the outflow, and that actually acts to stratify the outflow. And what that does is it modifies the outflow temperature as a function of radius. And the outflow temperature is important energetically for the efficiency of a hurricane. And so what this acts to do essentially is to make the outflow temperature increase with radius, which decreases the thermodynamic efficiency as a function of radius. And so it actually directly translates to a decrease in the wind field in the wind speed with radius. So you can refer to the paper for more details, but just as a basic introduction to the physics of that. So what does this solution look like? And so there's actually an analytical solution from this work, which is the angular momentum, and it's defined relative to its value at the radius of maximum wind. And so I just put the form up here. It's a function of the radius as a function, or of the radius normalized by the radius of maximum wind. And so it takes in as parameters Rmax and Vmax. And then you also need F to define the angular momentum. So F is the Coriolis parameter. And then it has one environmental parameter, which is the CK over CD, which is the ratio of the exchange coefficients of enthalpy and momentum at the surface. So as I said, surface exchange is very important. And so what this parameter does is, so it's plotted here, is examples of the profile, what the wind profile looks like for different values of CK over CD. And so what this parameter is doing is, as you increase its value, it acts to narrow the wind field relative to the radius of maximum wind. So it controls the breadth of the vortex in this vicinity.
Which one is the point on this?
It's a great question. I'll get to that, but we don't know, is the short answer. And I should point out this solution, the analytical solution, ignores the effects of dissipative heating as well as the pressure dependence of saturation enthalpy. So there's a couple of important effects that are not accounted for in this. But it's a nice analytical solution, which is nice to work with. OK, so next we have an outer descending solution from a manual 2004 originally. And it's called descending because it's valid in the region where there's no deep convection and air is simply gradually subsiding under the influence of radiative cooling. And so that's what this schematic is showing, is that basically you have some radiative subsidence rate under the influence of radiative cooling, that air is very gradually subsiding. And this actually is assumed to have to balance the Ekman suction rate into the top of the boundary layer that's associated with the boundary layer flow, which has negative vorticity in the outer region under the influence of friction. So it's sort of an elegant solution that basically combines the dynamics of a simple boundary layer to the thermodynamics of the free troposphere. And so what does this look like? So what this is it's not an explicit analytical solution, but oops, I think I've killed this thing. Oh, there we go. But it's actually a differential equation that doesn't have an analytical solution, as far as anyone I know knows, or me, for all the time I've spent trying to figure one out. So just put it up here. And so it's a quantity, it defines the distribution, or how the angular momentum varies with radius, basically. And so it takes as parameters R0, which is the outer radius, the radius where the winds go to 0, and then F again. And then it has another two environmental parameters, the drag coefficient, and then this radiative subsidence rate. It's actually their ratio that's in the solution. And so examples are shown on the right. And I should say, the drag coefficient I work with, I just specify it to be a function of wind speed following data from Donnellan et al. 2004. So we have estimates of what the drag coefficient should be as a function of wind speed. So that leaves the radiative subsidence rate, W cool, as a parameter that we'd like to have a value for. So we can look at the sensitivity of that. And so what you see is this: you have this tail solution, and then how quickly or slowly the wind speed changes with radius depends somewhat on this radiative subsidence rate here for 3 different values there. So we'll come back to that. OK, so what's nice is that we have two solutions that exist, and they apply for two distinct thermodynamic regimes: this inner ascending model and then an outer descending model. And so a question is, can we just stick them together? Because that would be sort of a first guess of what the structure of a hurricane might look like. And it turns out that you can. And you can just stick them together, and there's a unique merge point, which is shown here by this red X, for basically any value of every parameter. And you can actually show mathematically that there's always a unique merge point. And so what is kind of remarkable, and whether it's fundamental or coincidental isn't really clear, but the fact is that you can do it. And it gives you a complete wind profile. And in particular, it has this property that we're interested in, which is to have this rapid decrease beyond our max, and then this long tail at larger radii. And so that's nice. And so conceptually, what's also nice is that it aligns with the way, or like a basic physical understanding of hurricanes as an overturning circulation, which is where you have this narrow region where there's upward motion and strong upward motion, and then you have inflow and outflow below and above that, and then you have this very broad region of descent that's very gradual. And so implicitly in the solution is an overturning circulation, which is nice. OK, so we have this complete model for absolute angular momentum. And so we can look at our Katrina case and see how that compares. And of course, I picked a very nice case. And so what I've done here is the dashed lines represent the model comparison, where the inputs, we just give it Vmax and Rmax, and then F. So these are quantities that you might, in principle, have from, say, observations or in operational work. Set the radiative substance rate to 2 millimeters per second, and then say CK over CD to be 1, which is just kind of a common number that's taken. And so what you get is that just with these parameters, you get a pretty darn good fit, which is pretty nice. And so I just want to point out, so where does this 2 millimeters per second come from? Is that a reasonable number? And so if you just assume a moist adiabatic atmosphere at 302 Kelvin sea surface temperature with an 80% surface relative humidity, and then 1 Kelvin per day radiative cooling in the free troposphere, which is a characteristic value, you'll get something that's about 2 millimeters per second. So physically, this is something that we would expect, and there's been a couple other studies recently that have just looked in radiative convective equilibrium, what you get for this radiative subsidence rate, and including our own work with Kevin Reed here. And you get something in this ballpark, so something like 2 millimeters per second. So it seems like a reasonable value, and it's giving us something that can reproduce this outer circulation. And just to point out that this is really a very broad region. This is 600 kilometers wide annulus around the storm. And so it seems to suggest that it's really, this outer model is really doing quite a nice job of reproducing the actual outer circulation or characteristic outer circulation in a tropical cyclone. So we can look statistically, and I won't go into a ton of detail on this, but basically we can compare this with the entire H-wind data set, which the sample sizes, so this is broken down by Saffir-Simpson category, so by intensity from tropical storm up to category 4 and 5, and then the sample sizes are shown in parentheses. And so what's plotted here is the statistics of error as a function of radius normalized by the radius of maximum wind. And so it's the difference between the model and the error, and then the statistics of that quantity model, the model wind speed minus the minus data. And then the solid lines are the median, and the dashed lines are the interquartile range, and then the characteristic merge points are shown at the circles. And so first, I just want to say, so going back to Murat, you had asked, so CK over CD, basically, we don't know what it is. What we did was basically tried to come up with the best fit to see what value you get. So in some sense, keep treating it as a tuning parameter. And what you get is a value that's in the range of between 0.5 and 1, which is arguably the right order of magnitude. And this is basically the range of uncertainty in our understanding of what that value should be in reality. There's lots of people that work on that, and I don't claim to know a ton about all of the details of it. But you get something that's the right order of magnitude, though this range increases with intensity. It goes from 0.5, the best fit value goes from 0.5 at lower intensity up to 1 at higher intensity, which is arguably the opposite of what people have seen in terms of best fit estimates from observations. So for our purposes, it's sort of mostly just a tuning parameter, and it doesn't have a huge dependence on the outcome, but it does still govern the width of the wind field in the vicinity of the radius of maximum wind. So. OK, so going back for the errors, so this is just taking our model and looking at the statistics of errors. And you find that it does a pretty good job overall, though there's this residual underestimation at intermediate radii. But it actually works pretty well across all intensities. And so I can show this maybe a little bit more clearly. This is just looking at the median profile, the median observed profile, and then fitting the model to that, or putting the model on and comparing it there, where you see that it does a good job in the inner region, and then you have this residual underestimation. But when you get to large radii, it ends up returning to being approximately unbiased at large radii. So we have this underestimation, and so just as a hypothesis for why we're getting that, one potential explanation is the role of intermittent convection. So basically, the model, as it is assuming that there's strong convection in the inner region, and then it immediately shifts to no convection outside of it. And in reality, that's not really what happens usually. Usually, you tend to have convection that decays over some length scale, maybe relatively rapidly, but not instantaneously. So what this is showing here is, so the QuickScat data set actually also includes a quantity proportional to rain rate. So we can just look at the radial structure of rainfall. And so what this shows is how is rainfall normalized by its maximum value as a function of the radius normalized by the radius of maximum wind. And so this is to say that you can see convection is very strong near the radius of maximum wind and out to maybe 2 radii of maximum winds, and then it drops off very rapidly from there. But it doesn't go to 0 immediately. And these red X's are the merge point from this set of cases in my model. And so I just said this. So strong convection inside of the merge point, and then intermittent convection beyond that in some generalized sense. So it doesn't go to 0 immediately. But we know that convection outside of the inner core of the storm, people have shown this, can help enhance the inward import of angular momentum. And so that would help to spin up the winds above and beyond what you would expect if there was no rain at all. So this is just a hypothesis for what's going on in terms of why the wind profile seems to underestimate the winds at intermediate radii. OK, so just to summarize this section, this is basically a novel physical model, but a nice, simple, relatively simple analytical model for the complete radial structure of the wind field in a tropical cyclone. Is again merging this inner ascending region and outer descending region solutions. And it seems like nature may not be too far off. And I'll talk about other limitations at the end. I mean, there's certainly plenty of limitations here. But the fact that it does reasonably well is kind of remarkable, in my opinion, because, like I said, we're just sort of sticking 2 solutions together, and it doesn't do that bad. And then again, mentioned this potential role for, say, spiral rain bands in terms of this underestimation at intermediate radii. So, OK, so that's structure. So we have a model for structure. And so now we'd like to understand how can we use this model to understand wind field variability. And so for that, I'm going to start off just with a figure skater, because my goal is to use this model to help people think about hurricanes in the context of angular momentum and not wind field, and not the winds itself. And so thinking about the figure skater is the one thing that people seem to understand when you talk about the concept of angular momentum, this idea that the figure skater pulls their arms in and spins faster. So, so what do I mean in the context of a hurricane? So this is going back to this is the model idealized view of the winds and the radial distribution of the winds and angular momentum, where again, angular momentum has this hurricane component and then the earth component. And so this is relatively straightforward, but just at a given radius, a larger wind speed requires a larger value of angular momentum. And latitude, I see. And this larger value of m has to come from larger radii. M increases with radius, and it has to, otherwise it's inertially unstable. And so these larger values of m have to come from larger radii. So there's this inherent radial correlation in how the system has to evolve. And in particular, at the end of the day, the storm is using angular momentum that comes from the Earth itself. So in particular, you can think of the outer radius as essentially a source radius of angular momentum, where all of the angular momentum is from the rotation of the Earth alone. And so the Earth is really supplying the angular momentum for the system. This is why we don't have hurricanes on the equator. Well, one of the reasons why. And so really, in the end of the day, the story for the hurricane is that things have to come from the outside in. And so you can think of them starting from the outer radius. So if you wanted to, think from a Lagrangian perspective, if you're an air parcel, and you start at the outer radius, and you head radially inward towards the radius of maximum wind, you start with some amount of angular momentum from the Earth, and then by the time you get to the radius of maximum wind, you're gradually losing it to surface friction, and at the end you get to the radius of maximum wind, and you have some fraction that you have conserved, some fraction remaining from what you started with. And so this is sort of an alternative perspective of the way of thinking about size and structure. That this is, in terms of angular momentum, the size. So you can think of just R naught as size, or M naught. And then structure is basically how much angular momentum you lose between what you started with and the radius of maximum wind. So what's nice is that this model, we specified it with the radius of maximum wind, but really it needs some radius in the system. It needs some absolute length scale. So you can give it the outer radius instead of the radius of maximum wind. And you can ask, how does this model then represent the variability in the wind field from this perspective? And so what's nice is that because we have analytical solutions for these, you can actually show that if you're given values of these environmental parameters, which we have estimates for, that this structural quantity, M max over M naught, depends actually on two storm parameters. So the intensity, V max, and then there's another velocity scale that's actually given by the product of the Coriolis parameter and the outer radius. So these are both velocity scales. And that's what's plotted here. And then theoretically, this M max over M naught is the structural quantity, the fraction of angular momentum that you conserved. And this shows theoretically what the model predicts for the dependence of this fraction on these two quantities. So as you increase intensity, or as I should say, so as you increase intensity or you increase either size or latitude, you lose a larger fraction of your angular momentum that you started with by the time you get to the radius of maximum wind. And so you can look in observations as well. So this is, again, similar observations, but we're looking at this from a different perspective. And you see a very similar pattern. So this is from H-wind, where I'm working with calculating the outer radius from the radius of 12 meters per second. And so you get this very similar pattern where as you increase intensity or you increase this parameter FR naught in this direction, you get this decrease in this quantity M max over M naught. So it seems to show up in observations as well. So again, this is sort of a different way to think about testing the model and saying, what can the model tell us about the structure of the system, but from really purely an angular momentum perspective. OK, so so what are the implications then for the wind field? So we basically have M naught depends on R naught and F, and then the structural quantity depends on R naught and F as well as V max. So we have basically three parameters here to play with that we can look at. And so we want to relate this back to our original, what I talked about at the beginning about how does the wind field vary in nature. So three relevant parameters. And I'm going to focus specifically on intensity and size because that is what I mentioned as dominant modes at the beginning, modes of variability. So we can now go back to the wind field. So here we're varying the outer radius and keeping everything else constant. Where I varied the outer radius from 200 to 1,600 kilometers. This is just a bunch of model profiles for what you get for a constant intensity in F. And so what you get is this consistent rescaling of the wind field at all radii. So and it doesn't rescale uniformly. It's not just everything is multiplied by a factor of 2 or something like that. It rescales in a way that's given by the model. But there is a monotonic rescaling. And so this is something that hopefully is reminiscent of what we saw before, which is the way that the wind field tends to vary, where you have this consistent structure but at different sizes that we see in observations. So again, this is this variability mode number 1 in size. Is something that the model can reproduce. And then additionally, we can look at what happens when you vary the intensity of the storm. And so I'm showing this now both in terms of the wind and then also angular momentum. And so this is angular momentum normalized by its value at the outer radius. And so what you see here is this case where, so here size and F are constant, and then you vary intensity. And what you get is that the radius of maximum wind contracts inwards. And so you're having this significant variability in the inner circulation. And this is all relative actually to a fixed outer circulation. So the outer circulation doesn't care at all what's going on. And from the angular momentum perspective, what this corresponds to is this radial inward contraction of angular momentum surfaces. So angular momentum has to be drawn radially inward. And so physically, this is what we know has to happen associated with intensification in this case. And so, yeah, so as I mentioned, this outer circulation, however you look at it, the outer circulation doesn't seem to care what's going on. And so again, this harks back to what we've shown for the second mode of variability, which is this notion that the inner circulation can vary, particularly Rmax and Vmax, relative to a stable outer circulation. And so that's something that we've known for a while can happen. And what's remarkable is this two-region model is actually able to reproduce this notion of independent variability of the two regions. So yeah, just to summarize this. So given an outer radius, the model, or some measure of the outer circulation, the model variability can mirror what we see in nature. And so in particular, you have this more theoretical quantity, this dependence of this ratio, or the fraction of angular momentum you conserve at the radius of maximum wind from what you started with on these two parameters, Vmax and Fr0. They're two velocity scales. And that seemed to show up relatively well in observations as well. And then in terms of just the wind field itself, we have this intrastorm variability. I didn't actually explain this. This type of variability tends to occur predominantly within the life cycle of a storm, is that the inner structure varies relative to a stable outer region. And then what's characteristic across storms more often is the size of the entire storm tends to vary. So that you can have a small storm and a big storm, and we see that frequently. They can have the same intensity, same everything, but have very different sizes. And something I've spent a lot of time working on, but I'm not going to talk about here. So we have this nice structural model, and so what it leaves open is still this size parameter. So how does that vary? And that's something that we know it varies a lot in nature. It's really still ongoing work, and so I'm not going to spend time talking about that here, but I'm happy to talk about that offline. So okay, so just to put this together, so I guess I'm doing it right on time. So the objective really at the outset was a physical model for the complete structure as well as the variability in the wind field. And I think one thing I guess I didn't say at the beginning, but I should have, is that we have existing models for the wind field out there, but they tend to be either partially or totally statistical in nature. So people have done things like a double exponential profile, something like that, which is nice for practical purposes. But one of the things is that when it doesn't have physics in it, it's hard to say, does that model, when you train it on historical data, then apply to, say, a different climate state or something like that. And so, so having really a model that has physics embedded within it is really advantageous for understanding the actual physical phenomenon and how that might be affected by changes in, say, the climate system. So anyways, so yeah, our goal was to come up with a physical model for the complete structure. And it's one that combines this inner convecting region model and an outer non-convecting region model. And it's able to do that, and you can just stick them together. And it's not clear why that is, but it seems to do a pretty good job. And then this model is also capable of reproducing the wind field variability that we see in nature, which is this Mmax over M0, and then structure and size variability. And then really, just in general, this idea, I hope, is to get people to think of the figure skater, is that we focus on the wind field, but really what's more fundamental is angular momentum. And that's something that has a lot more, because it's a fundamental quantity and it's something that's conserved away from boundaries, has a lot more constraints on it than the wind field itself. And so that's something that I'm hoping to impress upon people moving forward. And in particular, that as part of that is that Earth is ultimately supplying this angular momentum from afar. And so this is something where, even though from a damage perspective, we may not care about the wind field, where it's 10 meters per second at 800 kilometers from the center of the storm. But physically, what's going on in the inner region where the winds are very strong has to depend to some extent on what's going on in the outer region, because that's where the angular momentum that it's using is coming from. So it's all one holistic system. And so having a model for the whole system is helpful for trying to understand details within it, such as the inner core wind field. I'm hoping that, so as just some notes, is that the size and these terms size and structure are often thrown around sort of interchangeably. And so I'm hoping that this model can help give a little bit of a better understanding of the difference, these terms, size and structure, and so in particular this notion that when we talk about size, we talk about, say, the radius of maximum wind, that is a very different implication for how that varies versus something like the radius of 12 meters per second in the outside of the circulation. So that's important. Another thing to point out is that this, from a physical perspective, this entire solution is actually governed by information from aloft. So in the inner region, it cares about turbulence, in the upper troposphere, and then the outer region cares about radiative cooling. And so this is sort of, I think, a kind of an interesting and remarkable facet, is that this, should this model be really true, that it basically says that things depend, that the wind field of a hurricane really depends on things not related to the boundary layer at all, to some extent. And so that's, I think, is kind of a remarkable thing, because a lot of people work on this and they focus on the boundary layer. And certainly the boundary layer plays a role in say, for example, transient variability in the wind field. But this is an equilibrium solution that says that it actually cares first and foremost about things that are going on in the free troposphere. And then just in general, that the whole, I like to think that the whole is greater than the sum of the parts, that you get some of this, the ability to capture the variability in the wind field is really tied to the fact that you just stick these two parts together, but somehow the interplay of those two parts when they're stuck together gives you things that seems to reproduce what goes on in reality quite well. So those are the good things. I still want to highlight, though, there's really a lot of limitations that I wasn't really able to touch on. First is the role of the boundary layer. So basically taking a model that's supposed to be valid at the top of the boundary layer and then comparing it to winds near the surface, and how the boundary layer affects things in terms of mediating the wind speeds between the top of the boundary layer, which is always hard to define on its own, and then at the surface is something that I haven't even bothered to touch on. And a lot of work goes into trying to understand that, and so I sort of just skirted it because I think it's something that adds a lot of complexity to it, but it certainly could be important, particularly in the inner core of the storm where things are very, very noisy. I should add that the inner solution, the physics haven't really been thoroughly tested. It's a relatively new model, and the underlying assumptions of it, there's several of them, and they haven't really been thoroughly tested in a full three-dimensional model. So that's something that I'm interested in looking at. But so the inner solution here, I would argue, is relatively, it's at the least convenient for this purposes, but it's not obvious that the assumptions of it are necessarily valid for explaining how the actual inner core wind field works in the real world. And then additionally, on top of that, one of the issues is that in the inner core, there's a lot of other things going on relative to the outer region, because you have convection going on. We have this issue with this ratio of exchange coefficients, which isn't very well understood. There's potential for supergradient winds there. And then these other, the dissipative heating and pressure dependence of saturation enthalpy are real physical processes that we aren't accounting for here. And so how those affect things which operate in the real world but not in this idealized model may change the answer a little bit. So, and then, as I mentioned before, it's something we don't have temporal variability here. So this is about the characteristic modes of variability in the wind field. But you may have smaller scale or other processes that are going on that induce temporal variability in the wind field, such as something like an eye wall replacement cycle that this model isn't going to be able to account for. I've also just assumed that this radiative subsidence rate is just constant, which is nice, and there's physical reasons for why we think it won't vary too much in space and time in the tropics, but that doesn't mean it doesn't vary, and so how that varies, in particular varies with radius, is something that hasn't really been explored much. So, but a constant radiative subsidence rate seems to do a pretty good job at the outset. And then lastly, this low bias intermediate radii are the hypothesis for why that might be occurring, but still also could be other reasons for that. So, but yeah, overall, though, the model, I mean, it seems to capture a lot of the basic behavior of the wind field in the real world, which I think is kind of remarkable. It surprised me how much I think I was able to get out of this. So it seems to suggest that it's getting something essential about how hurricanes work, but certainly there's still a lot more to work in that direction. So with that, just say thanks and happy to take questions.
Could you go a couple slides?
Sure.
Yeah. No, next.
This one?
Yes. I think this is methodologically correct to assume that some conventional forms like pressure and momentum depends on both velocity and power not. But let's say that we change your dimension pressure will not change, but your value of V will change.
Okay, I mean, but it's just a general dependence. I mean, the functional relationship would change, but the
Yeah, but which means for this to work, only the ratio of those parameters is independent.
yeah, I suppose that's
Which is Rossby number.
true. Right, yeah, I mean, you can think of it as a Rossby number. Yeah.
There is no other dependence possible, because you cannot have a function which depends, the result of which depends which system of units you use.
Right.
So, which means that the dependence depends not on both, but only on the ratio of those parameters. There is no other way.
Interesting.
It's just basic.
No, I see what you're saying. That's true. Yeah, I'll have to think about that. That is a good point. And I've never really thought about that.
Any other questions? Yeah.
A couple of years ago, we did a study with Katrina trying to see the monster wave generated. So at that time, basically, we took Reanalysis wind and replaced it with H wind model. But we didn't know this one has been right. So my question is from the more practical side. Now you claim that you can figure out the path. So how, say, if I'm going to do another study, will you just throw out all the Reanalysis sort out and replace with this kind of model, or you sometimes say because once you get away from the H-wave part,
Right. You don't have
all
anything.
the other stuff.
Right.
So from the more practical side, I want to use the Oregon wind to do a wave study. How you going to do that?
But so you're saying if you have, so you start with the H wind and then, but you need the wind field everywhere, right? So you want, and you're saying you, right now you use Reanalysis?
Yeah, we use Reanalysis.
Okay.
So this is very, it's not a forecast, but it's a look back.
Right. Yeah, I mean, so basically you're asking, does the model,
With this one,
yeah, you're asking, does the Reanalysis properly capture the wind field? That's a good question. I don't know. I'm working with someone on that. So, and what we found is that or what he's, I think, preliminary found is that it does a decent job if you get far enough away. So, but that's, yeah, that's a great question. So.
Any other questions?
So if you normalize all your graphs with the Vmax, does the point of intersection for all the 13 or 31 hurricanes you had, would those coincide?
Wait, which point of intersection? So you're saying?
Between the inner and the outer, because you had.
Oh, like the point where they merge together?
Yeah, right.
No, they don't. They merge. That depends on kind of everything. So it's not so simple. That's where, like, yeah, just normalizing V by Vmax doesn't give you. It's not like all profiles collapse together or anything like that. So, and nor is it in the model. So it's, yeah, no.
Could you just redefine for us again what the definition of the relative angular momentum is? Because you've got a swirling mass of fluid where the density drops with elevation, but you're sort of assuming there's no vertical share in the tangential velocity, and then it suddenly stops on the top of the hurricane. So how do you define what is the angular momentum? Is there different layers?
Yeah. So this is just, I mean, yeah. So when I say angular momentum, I really mean per unit mass, and I'm just focused on the unit. I mean per unit mass.
Per unit mass.
And then and I'm focused only on the low-level wind field. So yeah, I'm ignoring variations in density, and then I'm not concerned with what's going on above
and
the boundary
really
layer.
cool. That sinking rate, now sinking rate, 2 millimeters a second. That's about 200 meters a day. Seems pretty tiny. That could never be measured, could it?
I don't know. So yeah, I haven't actually. I mean, in our modeling work, it shows up. I don't know if I mean, I would assume it shows up in Reanalysis, but I haven't actually seen. So could it be measured observationally? I don't know. I would probably not. I'm not sure.
So it seems that is that the parameters are Vmax and bow naught or and bow naught, and so in terms of climate change, what's the things that would potentially change? So Vmax would probably increase because of the potential intensity.
Right. Yes. I mean, we.
Yeah. So R naught is not very clear.
Correct. Right. So there's So there's the three components. So Vmax, we assume that potential intensity will go up a little bit, and so the strongest storms may get a little bit stronger. And then F depends on where storms are forming, which I don't think we fully understand how that will change. And then the R naught is size, and we don't even understand size really now, much less under climate change. So the work I've done in terms of looking at how that'll change under climate seems to suggest that it's not changing, but that it won't change in a future climate. But I mean, that's, there's been not a lot of work on that. So R naught, the size part is the part that we still really don't understand very well. We just know it varies a lot.
Actually, sort of question on that. So you define things by Vmax, but I assume that if you sort of, instead of thinking about Vmax, but you use Rmax, you can still, it's sort of implicit.
Yes.
Rmax and Vmax. So instead of saying Vmax F and R naught, you could have Rmax F and R naught.
Yes, so you could have Rmax. So the idea is, so I didn't really discuss that. So Rmax is difficult. It's hard to, it's in the inner core. It is hard to observe, and there's a lot of variability there. And in particular, it depends on Vmax. We know that Rmax and Vmax will tend to covary. And so what's nice about this size, something from the outer circulation, as we showed, is that tends to not vary with intensity. So you could totally use it. If we had Rmax, and you basically have independent models, or models for Vmax and Rmax, then Rmax works just fine as a size parameter. But Rmax is it's more difficult because it also depends on intensity. So Vmax and R naught are, in some sense, independent parameters.
Yeah, the reason I raised that is because potentially, if you have the same R naught, and in order for Vmax to increase, then it seems that Rmax has to decrease.
Right.
To go together.
Right.
And so for stronger storm, if R naught doesn't change, then it has to be smaller.
Correct.
In terms of in the core.
Correct, right. So the idea would be that, in general, the outer size doesn't vary too dramatically in time. So if you had a storm and you have some outer size, and then you have intensity, the model will predict how Rmax varies, basically. And so that's nice because otherwise you have to provide a separate model for Rmax, but then they're correlated, and that's annoying. So it sort of takes advantage of the fact that the outer circulation just it's independent, seems to be independent of intensity, and it also just doesn't vary too dramatically. So it's arguably even just like a practical concern. The outer size is easier to think about than the inner size.
Brian? Yeah, you mentioned the R naught, the unknown with that. I was just curious, is there, to tap that momentum field from the Earth from far, is there a certain synoptic pattern? Do we understand what storms can tap momentum from far away and bring in to make them larger versus other storms that are more? If you think of it from that perspective, is there a certain synoptic pattern or condition that would favor that?
Yeah, so you're asking basically like what synoptic patterns lead to a bigger or a smaller storm?
In the context of the real world,
right.
Where there's a background field and thinking about how we can bring momentum from afar.
Right.
And is there a certain configuration that would maximize?
Right. So yes, I mean, to rephrase, I mean, I would say you're saying, what pattern when the storm initially forms, is it big or small, and how does the synoptic pattern contribute to creating a bigger storm that can draw angular momentum from farther versus a smaller storm? Would you say that's yeah? So I mean, so that's not understood. It's understood in general that there's some relationship between some sort of initial disturbance size, potentially, and the size of the storm when it forms. So in the East Pacific, almost all the storms form from African easterly waves, and so they all tend to be comparably relatively small size storms. In the West Pacific, from the monsoon gyre, you can get a really gigantic storm, where the monsoon gyre, which is a very large precursor synoptic disturbance, can turn into basically a large tropical cyclone. So it's able to draw from very large areas. But then you can also get very small storms within it. So it's So the
I was thinking within the context of the Atlantic basin, where there's this distribution that you showed.
Right.
Very small system Charlie versus something where obviously there could be air parcels. Someone did trajectory models.
Right.
Lagrangian, thinking about the momentum that way,
Yeah.
there must be some fundamental difference in some flow pattern that brings things together.
Yeah.
Tracking them versus you're not doing that. So.
Yeah, yeah, absolutely. No, I think that's true. We don't understand it very well. That's one of the. It's a big open question: is what generates these variations in size, and we don't really know.
So I think with that we'll move on to lunch. But let's thank Dan one last time.
There's no real hours, but I can tell though if we're slipping a little bit because the progress won't be there. So that's the most important thing is that work hard and then you know it takes some time off. Well, no, I would take advantage of that. So we just gotta make progress and we gotta find our groove here, going through that. So
did you want to meet?
Well, I would only meet if there's something to talk about. So
right now the only thing I'm going to talk to change it, and that would be the only thing because
I'll be curious to hear what he says because I think once you talk to me, you'll realize that we have some challenges, and we have to figure out a way to get over those challenges. So let's do that first as soon as possible.
I was planning on talking to him today.
Yeah, and then we can go from there. But we have to get you set up in a way where you can get data and go through this process because it's not going to be easy.
Right.
But we need to know what we're up against first. Okay, yeah, please talk to So you made an appointment with Ed, or?
I emailed him. He hasn't emailed back,
Okay.
but I was just gonna stop by his office and